Okay. So first of all, I would like to thank Jan and David for inviting me to give a talk in this wonderful workshop. I have to say that I'm not an expert in stochastic thermodynamics. My working field is information geometry. And this presentation emerged actually from a discussion that I had together with, in conjunction with the workshop that David and Jessica organized, where we had a meeting and started to talk about this subject. And these were my talk is going to be a kind of write-up of that discussion that we had. So I'm going to start with some basic information geometric structures, just to give you an idea on what information geometry is about. Then I will focus on the Fisher-Rao gradient, Fisher-Rao metric and the corresponding gradients. And then I will address the question to what extent we can understand stochastic thermodynamics in terms of the Fisher-Rao metric. So the summary of information geometry will be basically on this slide. So we have seen a typical situation in information geometry is the following: you have the set of probability distributions, and you have some manifold embedded in that set, and then you have a point, and you project that point onto that manifold. We have seen such projections in Artemis' presentation. And the canonical measure for distance that allows you to project onto such a manifold is the Kullback-Leibler divergence. And this is also the divergence that Artemis was talking about. In order to have uniqueness and existence, you need a particular structure of that manifold F here. And typically it's a set of Gibbs measures, and then you can prove existence and uniqueness, and it turns out to be the maximum entropy projection, the maximum entropy estimate of the probability distribution P. So that's the variational description of a projection, and it has a lot of similarity to Hilbert space theory. There we also consider, in a Hilbert space, we consider a point and we project onto a linear subspace. And here it looks a little bit somewhat different, because this family here does not look linear, and the distance is not an L2 distance coming from an, is not a distance coming from inner product in the Hilbert space. But actually the connection to Hilbert space theory is much closer than it appears at first sight. First of all, the family F can actually be considered as a flat subspace in some sense. And also there's another very nice connection. In Hilbert space theory, you have two ways to describe projections. One is the variational way, which I just explained here, and another way is actually using orthogonality. So you connect basically the point with the subspace, and then you choose the point P hat to be the projection, which actually satisfies the condition that the geodesic between P and P hat intersects the family orthogonally. Okay, and that's an equivalent way to define projections. Let me refer to this as geodesic projection in Hilbert space theory. And it turns out that the same formulation of projections can be also done in information geometry. So you have two equivalent ways. One is with the variational, with the distance, and the other way is with geodesics and orthogonality. For orthogonality, in order to talk about orthogonality, we need a metric, an inner product, and that's the inner product here defined in the simplex. This is actually the Fisher metric. Then in order to talk about geodesics, as we can see here, we have two kinds of geodesics. And these are the two kinds. This is the so-called mixture geodesics. It corresponds to this line here. And this is the exponential geodesic. Oops, sorry. this is the exponential geodesic, which corresponds to, this exponential geodesic corresponds to this line here. And here's a cartoon of these two kinds of geodesics. As you can see, one is given by the usual convex combination of 2 points, and the other one is a multiplicative version of this convex combination. And because if you write down such an expression, you lose normalization. You have to renormalize. And this is the kind of connection between 2 points, which corresponds to the exponential geodesic. So one is called the E geodesic and one the M geodesic. So we have 3 structures here. This is the metric. It's referred to as, it's a Riemannian metric actually. And we have 2 kinds of affine connections. That's the differential geometric term. It's an affine connection that we have here, and the affine connections define geodesics. So we have 2 kinds of affine connections, and they are actually dual with respect to each other. So the triple here is the basic structure and information geometry. These 2 connections or notions of geodesics are dual with respect to the Fisher metric. So that's the structure. And I would like to actually emphasize here, because we talked a lot about Thales entropy, Thales relative entropy, how you get this one. So these 2 kinds of geodesics or affine connections are in one-to-one correspondence with this Kullback-Leibler divergence. So now what you can do, you can actually take a convex combination of the 2. So in addition to these convex combinations, you can actually combine these 2 kinds of geodesics, and you get another kind of geodesic, which is referred to in information geometry as the alpha geodesic. And that alpha geodesic is consistent or defines another kind of divergence. It's the alpha divergence or the Thales Q divergence. So this is another connection here. So let me come back to the Fisher-Rao metric. So why is the Fisher-Rao metric natural? So I'm going to give you a few arguments why we should go for it. So this is the simplex here. It's the definition of the simplex on finitely many states. And this is the tangent space. The tangent space is the set of all vectors for which the components, the sum of the components vanish. Now let's have a look at the Fisher-Rao metric. So this was the definition that I had previously. And you can actually interpret the Fisher-Rao metric in the following way. If you rewrite it this way, you see it's simply an L2 product. So this is a kind of integral over these, the product of these 2 quotients, and you integrate with respect to the base point. So that would be the base point. And the reason for this being natural is the following. So these objects live in the tangent space. So they are measures. So you cannot take X and Y are measures because they live in the tangent space. So you cannot just take the product of them. You have to interpret them as functions, because the L2 product is a product of functions. This is why you have to divide, and this is a discrete version of the Radon-Nikodym derivative. So you take the density of that tangent vector with respect to the base point, the density of this tangent vector with respect to the same base point. These are functions, and then you take simply the L2 product. So in other words, the Fisher-Rao metric is simply the L2 product from the right perspective. So there's another interpretation of it. If you actually map the simplex into the sphere by taking the square root of the components and then use the normal L2, the normal canonical inner product in Rn, then this becomes an isometry. So in other words, the simplex together with the Fisher-Rao metric is nothing but the metrically nothing but the sphere embedded in Rn. Okay, these are arguments in favor of the Fisher-Rao metric, and I previously mentioned that the Fisher-Rao metric was discovered as the only one that is invariant with respect to what was called Markov morphisms. So let's come to the gradients. What are gradients? I think it's important to, so I will ask the question whether or not stochastic thermodynamics can be described in terms of as a gradient flow. And for this, we have to clarify what we mean by gradient. Often people just mean the vector consisting of the partial derivatives. And this is actually not true. So for the gradient, this is the construction of a gradient. So I'm going to explain this. So you have a function defined on M. M is an arbitrary manifold, and that's the function you want to take the gradient of. So what you do is the following. You consider the linearization of that function. So it's no longer, the linearization is no longer defined on M itself, but on the tangent space, okay? And the tangent space, if you take a direction in this tangent space, that's denoted by X here, you simply take the derivative of L in the direction of X, okay? And as we know, if we take linear combinations of the directions, this will be translated linearly. So the derivative, the partial derivative of L in the direction of X plus Y will be the partial derivative of L in the direction of X plus the partial derivative of L in the direction of X, Y. So it's, in other words, it's a linear form. So this object is a linear form, okay? So that's the first step you make. You take the differential of a function. And now let's go to this picture here. So this is such a linear form. So this is the tangent space. And you have a linear form. This is why this is a linear. So that's the hyperplane touching at some point the graph of this function L. So it's a linearization of that function. And what you then do is the following. You consider this sphere around the point here. Because it's a tangent space, it's a linear space, you consider the sphere. So that's the set of all vectors, all directions X, for which the norm is 1, okay? And for this one, you actually need a notion of a norm. Or if you have a Riemannian structure, you need to know this, this inner product, okay? That's the norm. And once you have this sphere, you can actually optimize, maximize the linear form denoted by L here. So this L is the DLP. So that's the linear form. You maximize on this sphere the linear form, and then you get, in this case, you get this point, and this is the direction that you have to go. And you have to go in this direction in order to increase to that's the direction of maximal increase of the linearized version of L. So that's the definition of the gradient, okay? So to summarize, it is important to have a metric, a notion of a norm in order to define a gradient. You cannot just take the vector of partial derivatives. So let's come to Fisher gradients. So here's the formula for Fisher gradient. So if you have this function L now defined on the simplex, and it could be the entropy, it could be anything else, you take the vector of partial derivatives, which is here, but then you plug these partial derivatives in this formula. That's the proposition. It's telling you that the Fisher gradient, the gradient with respect to the Fisher-Rao metric, is computed according to this formula. And as you can see, if you take the sum over all I, this will cancel to 0, which means that this is in the tangent space here. So this works. So let's have an example, actually 3 simple examples. Let's have as the function L the entropy, the Shannon entropy. We use that formula. We write down the differential equation for this. That's the gradient differential equation. So we are looking for those curves whose derivatives velocities equal the gradient of h. So we want to maximize h, the entropy, and we start with p. And you can solve this, so you get as a solution this one here. And here is a drawing of the curves. You get the curves of these solutions. So if you start here,
so Nihat, we can't see a cursor or a pointer, so just be aware of that. We can see your slides.
That's really bad. So
if you see a top bar, there is a annotation.
So this,
and then there is a spotlight. Yes.
Okay, I'm so sorry for that.
Don't worry. Yes. Yes. Good. Now I see it. Now we see it.
We see it.
Okay. So here, if you start here, so as you can see, for t to infinity, this goes to 0. Pi to the 0 is 1. So this will be 1 over n. So you converge to the center of the simplex. And for t to minus infinity, this becomes actually a Dirac measure in most generically. So this is these are the curves that you get for the entropy. So now let's do it for the KL divergence. So you take the KL divergence, and it's a function of 2 arguments. So let's fix the first argument p, and consider it as a function with respect to the second argument, with respect to q. Then you can compute the Fisher-Rao gradient of the Kullback-Leibler divergence. So again, with respect to the second argument, and you get this nice difference field. That's a little bit, it looks very simple. It is simple. And if you solve for this, you get this normal convex combination of the 2 points. So if this is your initial point and you solve this equation, it will converge to the point which you plug in as the first argument initially in the Kullback-Leibler divergence. As it's not a coincidence that you get actually the M geodesic back here. So I was talking about the M geodesic in the beginning. And so if you take the gradient with respect to the second argument using the Fisher-Rao metric, you recover the M geodesic. And if you do the same thing now for the first argument, you fix the second argument q, consider the first argument as a variable, and compute the Fisher-Rao gradient. You get this quantity here. It looks more complicated, but it can also be interpreted as a kind of difference with respect to the exponential connection. And you can also solve it here, and you get, this time, you get the E geodesic. So these are the 2 kinds of geodesics that I was talking about on my first slide. And so for t to infinity, for t equals 0, this is p divided by q times q. So this is p. And for t to infinity, this converges to 0. Altogether, you get q as the limit point. So, and that's the E geodesic. So there is a deep connection between the notions of geodesics and the so-called canonical divergence and the Kullback-Leibler divergence. It is such a canonical divergence. And in a work from 2015, we, together with Amari, we explored this connection in order actually to define appropriate divergences for particular problems. Okay, these are the 3 examples I wanted to show to you. Now let's come to a test. So given a vector field, and the vector field looks like this, how can I test if this is actually a gradient field with respect to a Fisher-Rao metric, with respect to the Fisher-Rao metric? And there's simple test. You have that's the vector field, and you have to do this test here. Okay, I'm not going into the details. Let's apply this. And this brings me to stochastic thermodynamics. So we have the master equation here. And let's rewrite the master equation. So that's the vector field. Let's rewrite the vector field in this way so that it has this structure. And we define these functions to be the fi of p, and now we can do the test. If we do the test and we get this criterion. So if this is satisfied, then this will describe, this equation, the master equation, will describe a gradient flow. And actually, it's not. It has been highlighted several times. So the master equation is not given as a gradient in terms of a gradient field so I'm sorry. Do you hear this sound? I think it's in my house.
We do.
You do.
I don't hear anything.
It disappeared. Okay.
But just to let you know, you're basically you're in your question and answer period now.
Okay. So one important remark here: if you actually plug in or use the detailed balance equation here, the property, assume the detailed balance property, then so you would replace Wij_Pj by Wj_Ipi, and suddenly you get this term here. And the same with the second and third term, which means that in the point of detailed balance, you have actually equality. And this might explain why near the detailed balance, you can describe the system, this system here, approximately as a gradient flow with respect to the Fisher-Rao metric. It has been pointed out several times. Okay, let me come to, so these are the last two slides, I think, 2 or 3. Let me go quickly through them. So it turns out the solution is the following. The Fisher-Rao metric is not the right metric to take, and there's this seminal work of in which Felix Otto was involved and actually further developed. He's famous for this work. So you start with the stochastic differential equation, Otto differential equation. And the nice thing is here you start with the drift term that is given itself as a gradient. Okay, so it's Nabla psi, that's the drift term, and this is the diffusion term. And we derive from this the Fokker-Planck equation, the Kolmogorov forward equation, and of course we know that this is the unique stationary distribution. And now the question is, how can we describe this? This is the continuous analog of the master equation. And they proved already in this paper here that this can be actually described as a gradient flow, but with respect to the so-called Wasserstein distance. And the Wasserstein distance is defined as follows. It's the distance between two measures, mu1 and mu2. You basically take, you take on the product space probability distribution, P, and you integrate these differences here with respect to that distribution. And that distribution has to satisfy the following condition. The first marginal has to coincide with mu1, and the second marginal has to coincide with mu2. That's the condition. And then you take the infimum over all such distributions, okay? And it looks strange, but it gives you a Riemannian structure. And I think that's the Riemannian structure based on this Wasserstein distance has been worked out by Otto, and this is why it's referred to as Otto metric. So that's the analog of the Fisher-Rao metric. And I'm not going to go into the details, but just as a remark, so the Fisher-Rao metric was based on the L2 product between functions f and g. And the Otto metric turns out to be also based on something very familiar. It's again an L2 product of f and g, but in a different way. So you first take the gradient of f and then the gradient of g, and then take the inner product of the two gradient fields. It's again some kind of L2 product, and this metric gives you actually the Wasserstein distance, and it gives you the right metric in order to describe the Fokker-Planck equation. So this is just the theorem that I just described. So if you use that metric instead of the Fisher-Rao metric, then you can prove that the free energy is actually the right function, is optimized. through the Fokker-Planck equation. And this is the last statement. It's not really a theorem. This is just to say that later on, starting with 2011, people have extended this theory to finitely many states where you have the master equation. But it turns out to be even surprisingly more complicated than the continuous case. So that's my last statement. I just want to say, highlight one thing. I find the field very fascinating. And we have seen several talks on information geometry in the context of stochastic thermodynamics. And if you have work that you want to distribute within the community of information geometry related to stochastic thermodynamics, that would be the ideal journal, which we started a few years ago. Thank you very much.